So in this lesson we're going to start looking at the energy that's stored in capacitors. And one thing to point out is that in order to move charges in a capacitor, if you're moving charges in either a conductor or non-conductor, you have to do work in order to get them in an arrangement that is not, neutral charge. So the work that gets done gets stored as potential energy within the capacitor. So if you try to calculate what that work looks like, I'm going to call dW the amount of work that it takes to move one charge dq a distance or a voltage V prime. I'm using V prime and dq prime because we may not have fully charged the capacitor to V or fully used up all the Q. So if you plug in what V prime would look like, it would look like Q prime, how much charge we've already put on the capacitor, divided by the capacitance C. I could then integrate things, and well, if I want to fully charge the capacitor, I'm going to charge it up to Q. And what we end up with if we complete this integral is that it's Q squared over 2C. Now I can use the relationship that Q is equal to C times V to get that it's also equal to 1/2 C times V squared if I had it in terms of V and C. So these are two ways that I can calculate the potential energy. It happens to work out that if you actually play around with this a little bit, you find that the units work out to be joules if you play around with the units. So one problem that I think is pretty interesting to think about is this problem here. And what this problem really deals with is looking at how much energy is stored if you put charge on the outside of an object. Where this becomes useful is if you look at industries involving the transportation of powders, sparks can sometimes be very dangerous and disastrous. The picture that I've put at the right is actually an example of where a static electrical discharge ignited an aerosol powder to create, well, in this case, a gigantic explosion. This happened very, very close to us in Faribault, Minnesota, in Minneapolis, at the Washburn A mill. What is this? About 140 years ago, May 2nd, 1878. This happened to be one of the largest flour mill explosions really in the United States. And this was a catalyst to change a lot of rules about how you produce flour. You may not know it, but flour or other milled grains, their powder when they become aerosol happens to be highly explosive. It's actually more explosive than natural gas when contained in a contained building like this. This explosion was an explosion that was felt in downtown St. Paul, which is 15 to 20 miles away, and reduced the capacity of Minneapolis flour milling district by 1/3. It'd be worth pointing out that in 1878, Minneapolis was the largest flour milling town in the world by a fairly substantial margin. That would be true all the way until the 1950s. So what's true about a flour explosion like this is that a spark carrying as little as 150 millijoules of energy, which is not that much energy, can trigger an explosion. So let's assume that a person acts as a spherical capacitor with a radius of 1.8 meters, and we're going to treat them like an isolated sphere, and we want to know what type of voltage, or what voltage would I need to cause this type of explosion. So we're going to say the potential energy that I need to have stored is 150 millijoules, and 1.8 meters is the distance, or my radius. And so we can actually calculate the capacitance in that case. And once I know the capacitance, I can find the voltage. So really I can say voltage squared is equal to 2 times potential energy divided by capacitance. Or if I plug it in, all my values, I get that you need about 39,000 volts, which seems like a lot of energy, right? Until you consider the breakdown voltage of dry air. That dry air has a breakdown voltage of about 3,000 volts per millimeter. So this would be a spark that travels 13 millimeters or 1.3 centimeters. I guarantee you that all of you have experienced a static electrical spark which traveled more than 1.3 centimeters. And all of you have seen it because we saw multiple of them when I did the Van de Graaff generator demo. Our Van de Graaff generator can produce voltages up to 500,000 volts. So this is not an unreasonable amount of voltage to be created on a person's body. So let's look at a parallel plate capacitor and calculate the energy density within a parallel plate capacitor. And the way to do that would be to take energy and divide it by the volume of a parallel plate capacitor, or the volume inside there, area times distance. If we do a little bit of manipulation, we could put CV squared in there and divide it by 2A. I know C is related to epsilon naught A and D, and so if I kind of plug those things in, I see that it's related to V squared and D. I also know that E is related to V and D, and so I can also write the energy density in terms of E as well, that the electric field and the energy density are kind of proportional to one another. What this means is that the energy is really stored within the electric field inside the capacitor. So let's do a quick problem where I have an isolated sphere, and let's try to figure out what is the potential energy stored in this type of capacitor and what is the energy density at the surface of the sphere. So finding energy density is pretty easy. Q squared over 2C. I can find C for an isolated sphere, and so if I plug everything in, I get that the amount of energy stored in this sphere is 107 nanojoules. Now if I use that energy density is related to electric field, and I know what the electric field is for an isolated sphere at the surface of the sphere, it's essentially the electric field for a point charge, and if I plug that into my formula, or plug in really that electric field into this formula here, we end up with this expression for what the energy density is, which looks like a pretty small amount of energy, but remember, even small amounts of energy can do quite a bit of damage when we talk about electric fields. So this is kind of a quick overview of energy stored in capacitors and how we could use that information to solve some problems.